Generalization of Fermat's little theorem due to Euler. It states that if GCD of A and M is equal to 1, then A raised to phi of M is congruent to 1 modulo M. Proof. First, let us consider the case when M is a prime power. That is, let M is equal to P raised to alpha, where alpha greater than or equal to 1. Here we prove this case by induction on alpha. Let us consider the case when alpha is equal to 1. Then we know that A raised to phi of M equal to A raised to phi of P, and that is equal to A raised to P minus 1, and this is congruent to 1 modulo P or 1 modulo M using little theorem. So this theorem is true when alpha is equal to 1. Now let us assume that for our induction hypothesis that the result is true when M is equal to P raised to alpha minus 1. That is, we assume that A raised to phi of P raised to alpha minus 1 is congruent to 1 modulo P raised to alpha minus 1. That is, we have assumed that A raised to phi of P raised to alpha minus 1, which is equal to A raised to P raised to alpha minus 1 minus P raised to alpha minus 2 is congruent to 1 modulo P raised to alpha minus 1. We need to show that A raised to phi of P raised to alpha is also congruent to 1 modulo P raised to alpha. From this congruence relation, we have A raised to P raised to alpha minus 1 minus P raised to alpha minus 2 is equal to 1 plus a multiple of P raised to alpha minus 1. Since the LHS is congruent to 1 modulo P raised to alpha minus 1. Now we raise this quantity A raised to P raised to alpha minus 1 minus P raised to alpha minus 2 to the pth power. So that we get that is equal to 1 plus B into P raised to alpha minus 1 all raised to P. The left hand side is A raised to P raised to alpha minus P raised to alpha minus 1, which is A raised to phi of P raised to alpha itself, and that is equal to, the right hand side can be expanded using binomial theorem as 1 plus P into B into P raised to alpha minus 1 plus PC2 into the square of B into P raised to alpha minus 1 and so on, B into P raised to alpha minus 1 whole raised to P. We can see that the second term onwards are terms containing P raised to alpha. So this can be considered as 1 plus multiple of P raised to alpha. Therefore, we have obtained that A raised to phi of P raised to alpha, our LHS, is congruent to 1 modulo P raised to alpha. That is, we have obtained that A raised to phi of M is congruent to 1 modulo M when M is equal to P raised to alpha. Now, let us consider the case when M is not a power of prime. Then, by fundamental theorem of arithmetic, M can be expressed as a unique product of the form P1 raised to alpha 1 into P2 raised to alpha 2 into etc. PR raised to alpha R, where R is greater than or equal to 2 and P1, P2 etc. PR are distinct primes. Then we can see that phi of m will be equal to phi of p1 raised to alpha 1 into phi of p2 raised to alpha 2 into etc. phi of pr raised to alpha using the multiplicative property of phi. Since p1, p2, etc. pr are distinct primes, these numbers p1 raised to alpha 1, p2 raised to alpha 2, etc. pr raised to alpha are relatively prime to one another. So we can apply multiplicative property of phi here. Now using case 1, we can see that a raised to phi of p1 raised to alpha 1. Since p1 raised to alpha 1 is a power of the prime number p1. This is congruent to 1 modulo p1 raised to alpha 1. Similarly, a raised to phi of p2 raised to alpha 2 will be congruent to 1 modulo p2 raised to alpha 2 and so on. A raised to phi of pr raised to alpha r will be congruent to 1 modulo pr raised to alpha. This is a system of R congruences. Now let us consider the first congruence in that system, that is phi of p1 raised to alpha 1 congruent to 1 modulo p1 raised to alpha. Let us raise the two sides of this congruence to the phi of p2 raised to alpha 2 into etc. phi of pr raised to alpha power. Then we get a raised to phi of p1 raised to alpha 1 into phi of p2 raised to alpha 2 into etc. phi of pr raised to alpha r congruent to 1 modulo p1 raised to alpha. The left hand side is nothing but a raised to phi of m. And we have obtained that this is congruent to 1 modulo p1 raised to alpha 1. Similarly, if we consider the second congruence, that is a raised to phi of p2 raised to alpha 2 congruent to 1 modulo p2 raised to alpha 2 and raise both sides to the power phi of p1 raised to alpha 1 into phi of p3 raised to alpha 3 into etc. phi of pr raised to alpha r the power. Then we will obtain the relation a raised to phi of m congruent to 1 modulo p2 raised to alpha. Thus, we have obtained that a raised to phi of m is congruent to 1 modulo p1 raised to alpha 1, a raised to phi of m congruent to 1 modulo p2 raised to alpha 2 and so on. A raised to phi of m congruent to 1 modulo pr raised to alpha r if we apply the same procedure to the rth congruence from our system. Here we can observe that these moduli p1 raised to alpha 1, p2 raised to alpha 2 and so on, pr raised to alpha r are all relatively prime to one another. Now we know that a congruent to b modulo m and a congruent to b modulo n, where GCD of m and n is equal to 1, will imply that a congruent to b modulo mn. Applying the same result over here, we get a raised to phi of m congruent to 1 modulo p1 raised to alpha 1 into p2 raised to alpha 2 into etc. pr raised to alpha. That is, a raised to phi of m is congruent to 1 modulo this quantity is m itself. So we have obtained that a raised to phi of m is congruent to 1 modulo m as required by the statement of our theorem. Thus, we have proved that if m is any positive integer, then a raised to phi of m is congruent to 1 modulo m.